All right, to prepare you guys for lesson task number 10, or number 11, I'm sorry, we only have one more left. We're going to revisit some of the 9.1 and 9.2 notes. In particular, I don't really want to cover everything in 9.1 notes because that's up for your time to read and there's a lot of information. I want to talk about some of the problems and applications that we might come through or might observe. So let's go take a look at the applications in particular. And this was during the time I didn't have a stylus, so we can go through it with more detail. Let's suppose I had a question regarding planes in particular. And this plane right here, we can model the direction of it by a vector. Likewise, there's wind. Wind can be modeled by a vector as well. So this plane in particular heads due north 300 miles per hour and experience a 40 mile per hour crosswind flowing in the northeast direction, 30 degrees. These are our bearing angles. So be sure once you have your bearing angles, you need to figure out that angle measurement that you create for the direction of your vectors with the horizontal axis. So if I've already done that over here, I've shown that the vector u has an angle measurement or direction of 60 degrees. Just subtract 30 from 90. And vector v is actually very simple because it's going due north. We can put that with 90 degrees. Another thing you'll notice that these are directions and not really heights per se. So we don't have to really account for gravity in this type of problem. So we need to calculate in particular the true direction and true speed of the plane with that crosswind because the wind will affect the plane in some way and it will affect it in a direction and how fast it's going. So we model this normally with a parallelogram. We draw our two vectors and then the sum of these two vectors, we draw a parallelogram and then draw its corresponding diagonal. This is going to be something very important if you go into higher level maths. If you plan to take those, you should always draw your parallelograms when you're summing the two vectors to get the idea. All right. So I have these idea. Then I need to know what the vector v and u are. If I want to add them, I need to know their components. I'm given the direction and magnitudes, but not their components. So how do I do so? Well, first I list the magnitudes. The vector u for the wind is 40. Direction of the wind is 60 degrees. Then that means I can express it in terms of using polar form, if you remember. This r cosine theta, whatever direction of u in particular, it does matter. And then r sine theta, direction of u. Now, our modulus is actually called our magnitude in this case. So it's going to be the magnitude of u cosine theta u. And then magnitude of u sine theta of direction of u. So you need to have that filled in. And then we can actually just plug it in. We get 40 cosine of 60 degrees. Make sure your calculator is in degree mode. 40 sine 60 degrees. Why are we doing this? We need the components of u and we need the components of v to sum them. So first, let's calculate the components. I've already calculated that. We get 20 and 20 root 3. So that is nice. We have the components for u. This is the components, or this is the location of the endpoint of our vector if we position it at the origin. Well, you can choose to put it in I or j. That's up to you. The book puts it in terms of unit vectors I and j, which is perfectly fine. But I'm going to calculate the vector v now. The vector v in particular is going due north. My magnitude is 300. But then now I need to figure out the direction of it, and it's due north, which is 90 degrees. And then 300 sine 90 degrees. And if we calculate it, cosine of 90 is 0, so really we only get the jth component, which the jth component is going to be 300. Now I need to add them together. U plus v is going to be equal to, or this is w is equal to this. Our vector w, which is the sum, we get 20, 300 plus 20 root 3. We can approximate that if you would like to. 20 comma, that decimal is going to be, did I choose to approximate it? I did not choose to approximate it. Oh well. Well, that does not tell us the true direction, true speed. That just gives us the vector where our plane is going to go. So to get the direction and true speed, Well, calculate the magnitude. That'll calculate the true speed. The magnitude is calculated as 20 squared plus the component squared and square rooted. Sum the component squared, then square root. And it might be easier if you use decimals here. It's perfectly fine. You get the magnitude is roughly around 335.2 miles an hour. So we have the magnitude. Great. That is the true speed of the plane. To get the true direction of the plane, you can do a few things. So we can either set our components equal to the magnitude times cosine theta, 300 plus 20 root v, or 3, I'm sorry, is equal to the magnitude of v sine theta, which theta is in the direction of w. Which this might not help us as much, but it can, because then we can solve for theta in particular. Another way you can do this is you can also realize that, hey, if we're dealing with cosine and sine at the same time, why not just do tangent of theta, direction of w? Well, that's just your y component or your second component divided by your first component. So I can just do 300 or 300 plus 20 root 3 over 20. If I wanted to calculate for this theta, I need to do the arctan or tan inverse function. If you put in your calculator, let's go ahead and do that. And I'm going to work in degree mode because I want my angle measurement in degrees per se. Let's do that. Let's do tan inverse of 300 plus 20 square root 3, all divided by, what's that, by 20. So you get the angle measurement, the direction to be approximately 86.58 degrees. Now, is this the actual angle measurement? Well, you have to be careful. When you solve for your angle measurement, you have to know what quadrant your angle should live in. It is very important. Notice that my components of W, these are my components, they're both positive. So my angle measurement better live in the first quadrant. Quadrant still matters. And in this case, 86.58 degrees is in the first quadrant, so I can say 86.58 degrees is the direction, the true direction of the plane after the air currents or the wind. So that covers it for 9.1, how to sum vectors and whatnot, how to calculate all of these information. Then let's go with 9.2. So 9.2 is all about the dot product. Dot product, you're just going to multiply the components and then sum the components and you get a scalar. So moving down, you work with something called, or the dot product in particular relates the product of the magnitude. If the vectors are different, then we have this cosine theta we need to deal with if they're different. So in particular, we have a formula for that. And then later on, we're going to be working with the component of u along v. The component of u along v. I struggle with working with this, so I always write it as a function so I know what I'm talking about. So in particular, in this picture, you want to throw the vector u right here, the vector u, into the space of vector v. I want to see that distance it creates. So pretty much it's the idea of, hey, if I drop this 90-degree angle, how long is that vector u in the direction of v? Because I changed the direction. So the calculation is the magnitude of u times cosine theta. Theta is the angle between u and v. However, I'm not always going to give you the angle between the two vectors. That's not always the case. So you have to work around that. How can I work around it? Well, we have problems where we can calculate, showing some math and whatnot. You can show that if I replace this cosine theta with my previous dot product cosine theta definition, it's in your definition, it is actually just u dot v divided by the magnitude of u times the magnitude of v. Now notice that if I organize all this, I can cancel out the magnitudes of u because they're scalars, not vectors. They're scalars, I can cancel them out. Then I have the vector u dotted with the vector v divided by the magnitude of v. This is very important. The idea is that, hey, I want to put u in the direction of v, so I'm going to dot it with v. That'll put me in the same direction as v. However, I do not want the scale of v to affect my actual components, because v is a very long line. I don't want it to be just as long as v. That serves no purpose at all. I don't want it to contain all of this line. So what I do instead is I turn v into a magnitude of 1. How do I do so? I divide the vector v by the magnitude of v. I just divide by how long it is. That way it'll have a magnitude of 1. So that way I only get the direction. I get the vector u, put it in the direction of v, and I'm happy. And you can practice calculations with that. All right? Main thing you need to know, the component of u along v is a scalar. It is a scalar. I treat it as a function where my input is the vector u, because that makes it easier for me to work with this. Now, component of u along v, what's the difference between that and the new thing which is called the projection of u along v? The projection of u along v is like a shadow. I have the same idea, but I want to project that vector u onto the space v. It creates this little shadow idea. Now, the main difference between component of u along v and the projection of u along v is that the projection of u along v is a vector, not the magnitude. It is the vector. It has the magnitude of the component of u along v. It has that magnitude. Clearly, that distance has to be the component piece. So it has that magnitude. It's just turned into a vector. How do we turn this to a vector? Well, we're using the exact same definition as the component of u along v. Exact same thing right here. Boom. The only thing is I want the vector form. So how do I turn it into a vector? Well, it's a scalar. To turn it into a vector, I need to multiply it by a vector. Why would I multiply by any other vector besides v? Because v has that same direction. So I'm going to multiply by v. But again, we have that same story. I do not want it to be scaled by v, so I'm going to divide it by the magnitude of v, which is all of this piece right here. I multiply by a vector v to turn it into a vector, and I divide it by the magnitude of v. So then I have this nice formula where the dot product between u and v divided by the magnitude of v squared. This is all a scalar times the vector v. And that'll give me exactly the projection. And that is the length, or projection, which is a vector with length as the components of u along v. All right? And there's often time we need to resolve these vectors. It's not going to be necessarily in the lesson task, but it's just something you need to work with the review where, hey, I did all this magic and work and whatnot. I don't really like to call it magic, but I did all this work. But I need to explain my work. Resolving the vector means, hey, what orthogonal vectors did you split u into? In particular, when I did the projection of u along v, I broke it up into two orthogonal vectors, this piece and this piece. So the idea is that I just need to show you what those vectors are. I need to show you that they add up to the vector u, because that's how I constructed it. So boom, I list them as u1, u2. Boom, the dot product should be 0 clearly because they're orthogonal. And the last thing is work. We can calculate work as the force vector dot product with the displacement vector. Displacement is normally a scalar, but we can also have a vector that represents the displacement in particular of how much the force is acting on your object, how much you traveled. So you just dot product them and you will get the amount of work. Well, when you dot product is a scalar. So work is a scalar. It could be a scalar such as 11 pounds or whatever. So be sure you have that down packed. And that covers it for the main gist of lesson task 11. Be sure to look over this before your lesson task Monday. I think a lot of you guys try to do it on Monday, which that's kind of procrastinating. And then fortunately, you don't grasp the material enough. All right. I will catch you later. We only have one more lesson test, so be sure to look out for that. I will catch you later. Take care. Bye.